Chapter 3.4 is a study about continuity. And though continuity is a new term to us in calculus, we have visited to a point continuity in the past. And it has to do with breaks in our functions, what kind of breaks can occur. And we're going to study, for example, holes, asymptotes, piecewise functions, and various other functions that may have sort of a break somewhere in the graph of the function. So this new word, continuity, or to say a function is continuous. When we're talking continuity, we're talking about no interruptions, and that makes sense, right? So basically we're looking for graphs that are unbroken, and if they are broken, there's some sort of hole, for example, some sort of gap or an asymptote, then we cannot say it's continuous. This is a little bit of a more formal definition. We're just going to kind of analyze each one of these three pieces for what it means to be continuous. So when we were studying limits before, what we would have oftentimes is a limit as x approaches 1, and you'd have 1 over x minus 1, for example. This is the function that you're trying to study, and sometimes what would happen is you would try direct substitution, so you would be observing this function and you would plug in some sort of x value for which you are approaching. In this case, you get an undefined. In order for it to be continuous, this would be an example of a graph that was not continuous. What they're basically saying here is that when you directly substitute in, your answer should be defined. Your limit should be defined. Okay? So this is, once again, in a case like this, no manipulations could have been done to this graph or to this function in order to get it defined. So in the last video, when we were talking evaluating limits analytically, what we had were some manipulations, and if nothing works out, then you have to say that the limit does not exist. So for it to be continuous, it has to exist. You have to eventually be able to directly substitute in, is basically what it's saying. Okay, and that's the statement right here. Here's an example when we're talking no breaks. So here's kind of a complete made up function of a graph that would not be continuous. You can see right here there's this gap or this break here. And if I were to ask you what is the limit as x approaches that value c of this function f of x, if you looked at and revisited the definition of the limit, what you would be asking yourself is what values, you could say this was, let's call this, well, let's just say this is 2 and this is 1. So if you were approaching it from the left and then from the right, what you're saying is these don't approach the same y value, right? From the left side, it's approaching approximately 2. From the right side, if you get closer and closer to this value c, as you approach c in the x values, what's y getting closer and closer to? Well, in the y value, it's getting closer and closer to 1. So this is an example of where the left and the right sides, when you approach that value c, aren't adding up. So the story just doesn't add up. You would write does not exist. Actually, when I look at this, you could plug in f of c and get 2. Okay, so f of c is 2 in this case. You do get a defined answer. The limit does not exist, so it did meet requirement 1 up here of the conditions, but it did not meet the requirements of 2 or 3. So in order for a function to be continuous, it has to meet all of those conditions that concern limits. Continuity on an open interval, a function is continuous over this interval if at each one of those points, at each value throughout this function, it is continuous, so it meets those conditions. I did want to look at, quickly revisit what open intervals mean versus closed intervals. And open intervals will be represented with those round brackets, and once again, these does not include finite bounds. It does not include those ends. So in this case, on a number line, it would be as though you have open circles. It's the equivalent of those open circles. And what that allows you to say is, you can infinitely get closer to 10, but you'll never actually reach 10. So what is the largest number in this interval? You couldn't actually ever say the largest number, because I could top it every single time by adding another 9 onto it. Okay, so brackets, closed intervals are when they include those endpoints. So for a closed interval, it would be just like up above here, except for you have those ends that are included, so you actually have a defined end. It's 10. What is the largest number in this interval? It's 10. There is no largest number in this interval. To get an idea of what this is going to look like, how are we going to use this new definition of continuity, and then how are we going to use the intervals, what I want you to do is look at this problem and trying to identify over what intervals this function is continuous. So I have graphed this function down here, and just to recognize that this line right here is a vertical asymptote, and that's how a lot of graphing calculators will portray a vertical asymptote. And as a reminder, I want you to just go way back to the parent functions that we've learned in the past. This is the parent inverse function, 1 over x, and the thing to know about that is that this function has two asymptotes, a vertical one and then a horizontal one, and they happen to lie right on the x and y axes. So here's your x and y axes. And so where those two asymptotes intersect is right at the origin. And what this function looks like when graphed is if you go over 1, up 1 from that origin, or back 1, down 1 from the origin, you're going to get 2 key points. What happens from this point, you know that your graph is going to start sprouting from it. Plug in any value, 0.5, 0.1, 0.2. What you're going to see is this graph shoots up towards that asymptote but never crosses it. And the end behavior, what do I do with this end? It's going to approach that horizontal asymptote and never cross it. Same thing here, plug in negative 0.5, negative 0.2 if you want to into this function. What you're going to see is this is going to be shooting down towards negative infinity, getting close to that vertical asymptote but never crossing it. And same thing with this, your end behavior is going to get close to that horizontal asymptote but never cross it. So if you were to subtract 1 from that x, so let's look at the function g of x. So directly attached to that x, you have subtracted 1. It does the opposite of it, you would think, horizontally. Remember, x is everything to do with horizontal. So basically what happens is this whole thing shifts over to the right 1. So you're going to go over 1, and this new it looks like an origin, right? But it's been shifted over. So your asymptotes and their intersection, or that origin point, has been shifted over. So from that you would go over 1, up 1, and then you would get closer and closer to those asymptotes. And I just want to show you that that is what this is. Okay, so having said that, what we're trying to observe is, where is this continuous? What you're going to notice is there is this one major break in the graph, otherwise it's ever flowing. There's no other breaks. So how you would write that is from negative infinity to 1. That's where it is continuous. But we're not going to include negative infinity because you could never ever reach negative infinity. And we're not going to include 1 because, well, it's broken at 1. So you can get closer and closer to 1, but you could never actually plug in 1 into this function, so we can't include that as part of a number that's being continuous here. And then to break it at 1, we're going to go from 1 to infinity. Okay, rounded brackets for both of those because they're open intervals. So what we have gone over are open, closed intervals, how we notate those and how we kind of use those, and we've also looked at the definition of continuity. There's two other definitions that we're going to start discussing now, and they're one-sided limits. There's two types, and we've kind of even discussed this before. When we were trying to observe limits, we were saying you approach this from the left side and the right side. What's the y doing from the left side and the right side as you get closer and closer to your x? So that's what one-sided limits are. You have a left-sided limit. It's what are we approaching as we get closer from the smaller numbers or from the left side. And it's notated like this. So don't let it be confused with if you had limit of, let's say, x approaching negative 2. That's definitely approaching negative 2. Versus if you had limit as x approaches and then 2 from the left side. So on that number line, you're going to be approaching 2 from the left side. Okay, so what's happening to a graph like this, for example, as you're getting closer and closer to that value 2 from the left? The right-sided limit is very similar, except for it's going to have that plus symbol as a subscript. So what you're doing is you're just asking what's happening in this graph as you're getting closer, closer and closer from the right. So what's happening with y values as you're approaching it from this side. This is exactly like what we did with the limits. It's nothing really different other than you're just taking it piece by piece, and you can observe the left individually and the right individually. But when you're looking for the limit, you can always set up those XY charts. You can always graph it and look at it visually. And then also we're going to start getting to this more intuitive type of thing, but that takes practice. So we're going to look at some of these. Bringing it back now to those piecewise functions. What I am going to say is we have this piecewise function right here, and I want to know what is the limit of our function as x approaches 2 from the left. Okay, so this one is going to be from the right. One way we said you can set up a chart. That's going to be as you're getting closer to 2 on that number line, you're going from the left, so you want numbers that are approaching it, getting larger and larger, but never actually achieving 2. So you're going to start studying what are those values. And hopefully what you can say is that's getting closer to 5. Over here, when you're going from the right, you're going to want 2.1, but even closer yet would be 2.01, even closer yet 2.001, and then from the right, what you're seeing is this thing is getting closer and closer to 1. So it's exactly like what we were doing before, except we're just asking what is this function behaving like, what are the y's behaving like and getting closer to. That's what that limit means. And then you have a defined number that you're trying to get closer to with the x's. How this function would look graphically, here you have this x squared plus 1, so that's just a parabola that's been raised from the origin up 1. For any x value that's less than 2, you would plug it into this function and be graphing. So that's what it's going to appear like. And the x value is less than 2, so all over here the graph is appearing like this. Here is just a linear equation, so notice that this linear equation, it's -1, so it has a slope of -1, and then a y-intercept of 0, 3. So up here would be where your y-intercept was. But we wouldn't be able to plot. If you plugged in 0 here, you wouldn't get 3 because you would have used this top equation. So it's going to take on that shape. So you'll see that none of these plot points are going to take on until you get to 2, and then you graph on there. So here is a major theorem. So we can say and define a limit, and once again, this isn't too new. We've thought this through before, but now we're just putting a definition on it and formal way of writing it. But we can say that a limit exists at L only if it's approaching that L from the left side and the right side. So when we looked at that kind of goofy graph like this, when we were saying let's approach C, we couldn't say that this limit occurred because the left and the right hand side were not doing the same thing. So these need to be matching up in order for you to claim that the limit at that particular place is going to be that defined number that you have found. So when will functions not be continuous? So think about this for a second. If you want to try to list out all the ways that it would not be continuous. And here they are. If you thought of piecewise functions, we just did one that had a major break in it, so it was not continuous. It had those places where the left side and the right side were not approaching the same things. Greatest integer value functions, we're going to look at those. Those are those that steppy one. Oops. So we're going to look at some more of those. Rational functions with holes and asymptotes. This is a major one. So when you come across holes and asymptotes, those are definite breaks. Okay. And then absolute values, we're going to look at something like this. But here's an example of the greatest integer function. And the greatest integer value function, what it does is it's going to take on, if you plugged in 1.1, for example, what it does is it resorts to what is the greatest integer or whole number that's less than or equal to the number that you just inputted. So we wouldn't want to go to 2. If you're on the number line here, we're at 1 and 2, and you go back to that whole number that's to the left. So in this case, you would be graphing 1.5, it would still be 1. 1.9, it'd still be 1. But at 2, it's going to be jumping up to 2. And then 2.1, and so on and so forth. So let's evaluate this function as x approaches not -2, but 2 from the left. So we're looking at this value 2, and we want to approach it from the left. So what are all the values? You could look at it graphically and say, well, hopefully you're seeing that it's just always 1. Otherwise, you could write yourself out a chart and think to yourself, all right, 1.9, that's going to resort back to 1. But they're always going to be 1. So this is just 1. We're going to be approaching it from the right is what that means. So we're going to be going from the right, take values that are getting closer to 2, and what you're going to always see is you can see it graphically, or you could use the function to its definition and come up with these values yourself in a chart. So this is going to be 2. And then finally, what is going to be the limit of this function as x approaches 2? So going back to this theorem, what we have just found is that the left and right hand limits do not equal the same, so actually I should say does not exist. This is the last thing that I'm going to have you consider in this section, and it is talking about removable discontinuity. This is a study of really focusing on rational functions, and what we have been able to do is figure out that the left and right is still approaching a certain limit, and so therefore a limit does exist, but when we have holes in rational functions. Yes, the continuity is broken there, but the limit still exists. So what we call that is the removable discontinuity, and those are where those holes occur where you have that common factor on top and bottom. This is that skill of using manipulations. It was either divide or factor out. We also use rationalizing, and we also use condensing of fractions. So here is an example, number 33, that asks you to find where is this continuous. So the first thing that you need to consider is really, is there any limits that don't exist? And also, are there any manipulations that had to be done? So if you looked at it graphically, we have a definite break at x equals 1. There appears to be an asymptote. So to confirm that, what I'm going to do first, though, is I'm going to say, is there any manipulations that I can do? Can I simplify this down at all? Is there any common factor on top and bottom? And it's not really a condensing problem. It's not a rational problem. You don't have a radical minus a radical or anything. So this really would be, can you factor anything out? And I hope you can see on the bottom you have a polynomial with a common factor of x. So I'm going to pull that out. I'm going to rewrite f of x equals, these factors on top and bottom will just reduce down to 1 over 1. So what we have is really the function f of x is equal to 1 over x minus 1. This is a hole at x equals 0. So you're going to take that and plug it back into here. We have 1 over 0 minus 1. You have 0 comma negative 1 is where your hole is, right? So that's what your calculator is not going to show you. You have to be careful. Don't just resort to graphing it and trying to figure out where is it continuous and not. You may need to look at the actual function and do manipulations. So I'm going to write the intervals over which this is continuous from negative infinity, and there's going to be a break. It is at that value of 0. Okay? And then from 0 to, and then from 0 to, we have this other break, this asymptote. And if you need to, go back to this function. You can't manipulate it anymore. That x minus 1 is problematic. You will get an undefined on the bottom, and so therefore it is not continuous. At that x equals, solve for it, add 1 to both sides, at x equals 1. So at x equals 1, try plugging it in up here too. These are exactly equivalent except for that one hole. So I'm going to break it at 1, and then from 1 until infinity it's going to be continuous. So there are your breaks. There is where you're continuous. Your homework are these number sets. What we have done is the definition of continuity, what makes a function continuous, and remember there are 3 requirements. Okay. We also looked at left and right-handed limits. Okay, we found out that it has to be approaching the same thing from the left and right in order for a limit to exist, and so that deals fully with continuity. And then we also looked at the removable type of discontinuity, which are those holes. You gotta watch out for those removable.